My name is James Milner. I'm a software engineer at a company called SitePen, who are actually based in the States, but everybody who works at SitePen kind of works remotely. So I'm based out of London, and we've got 5 of us based out of London, and everyone else is based out in the States. I'm also a Google developer expert for web technologies, and I blog at lockstone.io, and you can find me on Twitter at James L. Milner. So, I kind of wanted to start with this GIF because I think it kind of illustrates like a recurring theme or a recurring problem that we kind of see in web applications, which is kind of this idea of like jankiness or delayed reactions to user input. And this is problematic because obviously users get very frustrated very quickly. So if you're trying to interact with a page and you can't get the response in the time that you like, you might close the page, you might go to a competitor, you kind of might do all kinds of things. So yeah, as developers, I guess we would refer to this problem as a slow time to interactive, or we might refer to it as a slow first input delay. So that first input delay is essentially where the user loads a page and that first interaction takes an exceedingly long time to actually respond to the interaction. But so what's actually causing this issue, or what is this problem actually under the hood? Like what's going on, what causes that? And there are probably a few reasons, but one of the core reasons for this is ultimately just the amount of JavaScript, or the JavaScript that we have inside our applications. So in 2017, there was some research done that showed that the average page weight of JavaScript on a page was about 387 kilobytes. So extrapolating that to 2019, let's say about 400 kilobytes. So 400 kilobytes on the surface doesn't sound like a substantial size, right? Like we might ship images that are roughly that size, like a PNG or a JPEG. But the thing is that JavaScript is not directly comparable to a JPEG, or any kind of image. And the reason for that is that JavaScript has a few extra steps that we need to do to make it do what we want to do. So we've got the download step, which is obviously just transferring the JavaScript over the wire, so from the server to the client. So obviously the more latency we have, the longer that period is going to be, and the more JavaScript we have, the worse it's going to get. And the next 2 steps are interesting because people often forget about them, or they don't really talk about them very much, but you've got to actually pass that JavaScript. So you have to look at that JavaScript, take the tokens, and turn it into something that the compiler can use to turn it into an executable program. And then once we've done that, we have to actually compile it. And once we've compiled it, we actually have to execute it. So there's actually 3 steps that happen before the JavaScript is even running on the page. So that's why those two, like JavaScript is often overlooked, because it's not just the download time, it's the other steps that happen on top of that which are painful for users. And yeah, this is all kind of generally happening on the main thread, although there are some things that are happening in the browsers that negate that, which I'll come on to later and talk a bit more about. So yeah, this is a trace that I did of a popular website that I won't name, because it's just, my general point here is just to kind of show what's kind of out there in the wild, or what's actually happening on multiple web pages all across the web. So I profiled this for 12 seconds, and of those 12 seconds on my £2,000 laptop, 8.5 seconds of that was JavaScript, executing JavaScript. So my point generally is that there is a lot of JavaScript going on a lot of pages. And the problem with that is, like, sometimes we don't necessarily know what impact that actually has on users, especially users of varying network speeds or various processing speeds. So especially, for example, users on low-power devices, or users in emerging markets, that's going to be even worse because it takes longer to do things, essentially. And that's going to reduce our things like time to interactive, and it's going to reduce our things, it's going to increase our time to interactive, and it's going to increase things like first input delay, so that delay when the user first interacts with a web page. But let's kind of go into this a little bit more. So I've said the main thread, but let's kind of go into what I'm talking about when I say the main thread. the main thread in the browser is kind of where everything's happening. And you can kind of think of the main thread in the browser in JavaScript as an event loop. And the event loop's kind of just spinning around, waiting for things to happen. And a lot of things are happening in a web application, right? So we've got things like handling user input, performing styling, updating the DOM, reacting to timers, fetching data, performing state management, so updating state in our web app. These are all things that the event loop has to deal with and prioritize and handle in various ways. And it has to do that in a way that kind of moves between dealing with our kind of logic and business logic and also like rendering to the page. So it has to have a mechanism for handling that. And the event loop does quite well at this. So this is a diagram I've kind of lifted from a talk by a guy called Jake Archbold from Google. And it kind of just is a basic, slightly simplified version of like what's happening in the event loop. So what happens is like we have a task that might come in. So for example, this might be an event handler, or it might just be a timer or some state management, any kind of like JavaScript task that you can think of. So the task comes in, and that will run until it finishes. So until that task is complete, whether it takes 6 milliseconds or it takes 500 milliseconds, it's just going to keep executing that task. And eventually, once that's finished, it's going to release, and it's going to go back to just spinning around. And browsers generally try and render a frame every 16 milliseconds. So every 16 milliseconds, if it's not executing a task, it's going to just say, OK, well, I need to paint something to this. I'm going to check if I need to paint something to the screen. And what happens is this lever at the top just like comes around, and then we go into rendering a frame. So you see it says RAF here, and that's request animation frame. So that's a browser API which you can use to schedule work to happen before a paint. So you might want to do things like if you're updating some styling, or if you're doing loads of crazy animations, you probably want to do that just before the frame paints. And I'll kind of talk a little bit more about that later. But the next few steps are kind of the rendering steps. So this is where the browser actually is rendering something to the screen. So you've got the styling step, which is just like, even for example, like setting color to red would be like a styling step. The layout step, which is going to execute and check if the layout of the page has changed at all, and it's going to commit that, and then eventually it's going to paint that to the screen. And once that's done, releases back, and it goes back to executing JavaScript if it needs to, or it goes back to rendering a new frame, like whatever needs to happen next. So yeah, this is the event loop, and that's kind of fundamentally at a basic level what's happening all the time in your web applications in the browser. There's kind of another interesting observation about the event loop is that there's a specification for the event loop, but some of the browsers kind of implement it slightly differently. So there's a really good GitHub repo by a guy called Alexander Totic, hope I pronounced his name right. And he basically goes through and he figures out what order different events run in. So for example, if you have a set timeout or a promise or a request animation frame, how do different browsers handle like different events and different orders that are chained? And the answer is that they all handle it very slightly differently, which means that the code that you're running in your browser, well, you probably already know this anyway, but code that you run is going to run slightly differently in every browser, just because of the way that they implement that event loop. Which is interesting, because it kind of like means that the code you write is not completely kind of deterministic, because every browser is going to handle it slightly differently. So that's the event loop. So the next thing I kind of want to talk about is relating this to user experience, and kind of bridge that gap between talking about the main thread and the event loop, and kind of bringing that back to the user. So let's dive into that a little bit more. So yeah, as I was saying, every 60 milliseconds, the browser is going to try and paint framed to the screen. And if there's work that's happening in the middle of when it wants to paint that frame, it's going to cause a delay. So it's going to cause this jank, it's going to cause this slowness. So that's kind of what we were seeing in that first GIF that I showed you was, well, something's happening on the main thread which is blocking the user input. So the user's trying to click on a button, and there's just, the event's being queued, but there's another event that's just blocking that main thread, and the user can't, like to them, it's just broken, like nothing's happening, right? So yeah, if you're doing these big synchronous tasks, it's going to block. So what you can do for this specific problem is you might want to chunk that up and maybe put it in some sort of, like you could do, you could chunk it up and put it in a set timeout, and technically that'll work because it'll just queue them as separate tasks, and in between those tasks can yield to the browser and it can render a new frame. But what kind of might make more sense is to use something like request animation frame, which I mentioned before, which can schedule those DOM updates and that styling to happen just before it paints the frame. And that's kind of like one way that you can solve that jankiness, especially when you're talking about kind of animations in particular, or talking about DOM updates and styling and that kind of work. But when you're kind of talking about general work that's maybe not necessarily targeting the DOM, there's kind of different things that you have to consider or different things you have to think about. So I already said about kind of chopping this up, so like chunking up work, but you also have to think of be a bit smarter about when that work is kind of executed. So for example, there's this concept of like lazy evaluation. So you could have some JavaScript logic that doesn't actually execute until it's needed. So if you have some JavaScript logic that only needs to happen on a click handler, you don't have to execute that, like you don't have to do that straight away. The next thing which I kind of talked about briefly was chunking using set timeout. And it sounds like really old school, and it sounds like a kind of, like, why are you using set timeout? Like, there's got to be a better way of doing it. But it's actually not a terrible solution. So if you do a set timeout with a function call and then just 0 seconds, then it will essentially turn that into a new task. So if you chunk up all that work, it's going to put them in separate tasks, and between those tasks, you can yield to the browser, you can respond to user input, you can render a new frame. But it's not really like kind of an ideal solution because it's not very smart. It's just kind of like batch up the work, but it doesn't necessarily say much about like when that work is being executed. So what we have in the browser now, I think most of the major browsers support this now, is this API called request idle callback. And if they don't, there's polyfills for it. So there's fallbacks that you can use. And what request idle callback does, in the same way that request animation frame schedules work to happen just before a frame commit, is request idle callback schedules work to happen in idle time. So when the browser's just sitting there twiddling its thumbs, you can set that work to be executing in that like idle time. And that's the perfect time to be executing work because the browser's not doing anything. So that means the rest of the time it can just be, the browser can be handling user input and it can be painting frames to the screen. So yeah, it's just about like this problem is that we have a lot of JavaScript, but it's also that we're often just having big batches of work that are running for like, tens, if not hundreds of milliseconds, and they're just stopping the user from doing anything. So if we kind of break this down a little bit, we can be a bit smarter about how we handle this. So there's this pattern that there's a guy called Philip Walton at Google, and he came up with this pattern which is called idle till urgent. And the main premise of this is that it kind of sidesteps some of the downsides that I was talking about with, or some of the downsides with lazy evaluation. So the problem is with lazy evaluation is it just offsets the work until the user needs to do that thing. But the problem is with that is that you are guaranteeing that the work that you need to do is happening as the user is trying to do something. So if it's a big task, you're guaranteeing that it's going to block the user. So what the concept of idle until urgent is that essentially you defer everything until idle time, so until the browser is just not doing much, unless the user immediately needs to do something, in which case you just return it instantaneously. So in the worst case, it has the same performance characteristics as lazy evaluation. In the best case, it's doing all the work when the user doesn't really care much about like what's happening on the page. So in theory, it's going to be better for preventing blocking user interactions. So next, I kind of want to talk about this concept of scheduling. And scheduling is something that we start to see gain more kind of traction in web development, even if not at the surface level. But inside kind of frameworks and libraries, scheduling has started to kind of take a foothold. So yeah, let's dive into it. Like, what is scheduling? So yeah, like I was saying, imagine we have a series of tasks. The interesting thing here is that not all work is equal, right? So loading analytics on your page is not as crucial as responding to a user interaction. So what we can do is we can say to the browser, or we can basically schedule our work so that the higher priority things happen first, and then anything else is just kind of like deferred until later or deferred until the browser is idle, for example, using something like request idle callback. So yeah, ultimately, what scheduling can be thought of as prioritizing certain types of work over other types of work in the browser. So a great example of this that's been happening for a little while is in Google Maps. So Google Maps has its own scheduler that is created using request animation frame. So it has kind of 4 bands of work. So it has input, animation, rendering, and something it just calls, like just lumps together called other. And the scheduler can schedule, for example, if you imagine you're panning around in Google Maps, what's going to be happening is it's going to be sending out requests for the surrounding tiles and doing all the animations to make sure, or like loading that into memory and all that kind of work. But if imagine that you clicked on one of these things you clicked on one of the restaurants on the left-hand side, you probably don't particularly want to be loading all the surrounding tiles and doing all the logic and work for loading all those surrounding tiles because you're not moving the map. So what the scheduler can do is it can prioritize the work that's happening or that's most critical to the user first. And this is great for like user experience. And it can also do clever things like, for example, when the map loads, so the browser's trying to run at 60 FPS, right? Every 60 milliseconds, it's trying to paint a frame. But like the average user is probably not going to notice if that drops slightly. So what it can do is it can throttle the FPS and then use more of that processing power to handle things. For example, at startup time, there's a lot of processing, a lot of work that needs to be done to do initialization and set up the Google Maps API. So it can throttle the rendering to 30 frames a second and then give more CPU time to like initialization work and things that need to be happening to allow the user to get going with Google Maps as quickly as possible, which is cool. And then kind of like from a framework perspective, we kind of started seeing multiple frameworks now taking scheduling or making scheduling like a core part of the framework. So I think, okay, so I'm going to preface this by saying I'm not a React expert. I'm not Dan Abramov, I'm probably not going to do this justice, but so in React, I think it was 16.3, they introduced this asynchronous rendering, time slicing, these are just the names that they've given it, which essentially allows for like scheduling and of chunking up of work and yielding to like frame renders or handling user interaction. So basically prioritization of work. It's kind of what we were talking about before. And we've seen similar things in frameworks such as Stencil, which you might have heard of. It's basically a framework that takes the approach of being more of a compiler than a framework. So it compiles things to native web components and tries to kind of remove as much kind of cruft as possible at the compile time rather than at runtime. And they have a concept of kind of scheduling using request idle callback. And also in a framework called Dojo, which is a framework I sometimes work on, and probably not as heavily as some of my colleagues, we have a very primitive version of scheduling, which again uses request idle callback where possible. Yeah, so that's kind of how frameworks are using scheduling, and kind of you can see why that might be critical for kind of prioritizing work that benefits users. So from a kind of standards perspective, so there was, I think in 2000, like last year, some of the developers at Google presented at something called TPAC, which is the kind of World Wide Web Consortium's, okay, I'm going to just read it off because I can't remember what it stands for, Technical Plenary and Advisory Committee meetings. This is kind of where they come together to talk about future standardizations. And they presented about a main thread scheduling API and what that kind of might look like. So there's no kind of finalized standards or anything, but it's kind of moving towards this idea that we need something in the browser that allows us to do this natively rather than just hacking together solutions with request idle callback or set timeout or request animation frame. We need like a native browser level API for scheduling work. That's going on. I think there's a GitHub repo where you can go and read all of this. It's quite cool. It's quite interesting. And it was updated about a month ago, so I think there's still it's still active and there's still stuff going on. And yeah, so then I was looking over my slides last night, and I was also not looking at my slides and looking at Twitter. And I came across this, which I was just like, oh, that's like unbelievably related to what I'm talking about today. So yeah, really fresh content literally from yesterday, which is this post from Facebook. And Facebook's been working with Chrome, and they've been working on this new scheduling API called isInputPending. And I can kind of see why Facebook React would want this, because it kind of ties together with what I was talking about with the React scheduling stuff. And so basically what the concept of isInputPending is like, if you imagine you have a scheduler that has a series of tasks, what it can do is it can say, if you have this isInputPending APIs, it can say, is there a current user input that's waiting to be processed? And if the answer is yes, then you can yield to the browser and you can let it handle the user input. If the answer is no, then you don't have to yield to the browser and you can just keep doing whatever it was, like whatever React does, like reconciling the virtual DOM or, yeah, I don't know what React does. So it can just go back to doing the work that it was doing before. So you can see why this API would definitely be helpful from kind of a framework perspective. Yeah, I mean, it could potentially be useful from a kind of general developer perspective, but I see it more as being critical for the kind of framework level stuff, or the library level stuff even. Okay, so now I'm going to talk about something slightly different, which is workers. And I'm going to kind of talk a bit about like how this might help offset some of the contention or majority of work that's happening kind of on the main thread. So what are workers, or web workers to give the full name? So I like this quote from MDN, which is, web workers make it possible to run a script in a background thread, allowing the main thread to run without being blocked or slowed down. So the cool thing that happens here is when you offload work to a web worker, the main thread is left just to do whatever it's left to do what it's good at, which is handling user input and rendering to the screen. So you can put all the other work off the main thread and keep that main thread free to be doing what it's good at. So kind of what does that look like? So for those of you who haven't seen what a worker looks like before, so what I've done here is I've done a little kind of, what's the word I'm looking for? I'm checking that it's available in the browser, and it should be because every workers are available in IE 10+. So what we do is create a new variable called worker, and then we just do the new worker, and then you point it at the script that you want to run in the worker. And then let's say, for example, that we have a DOM node, and then when we click on that DOM node, it fires a message. It passes some data to the worker to do some processing, whatever it might be, maybe some state management, send a fetch request, like update IndexedDB, whatever it might be. And then on the flip side, we can listen on the worker for messages that come back to the main thread from the worker thread. So that's what's going on the main thread in the main script. Word I was looking for was feature detection. So then next, let's have a little look what's happening in the worker script. So in worker land, things are slightly different. We don't have window. We have something called self, which refers to the worker itself. And then we can add an event listener for the message we've just sent from the main thread. So in the worker thread, we're just going to log out whatever was sent, and we're just going to post a message back saying that the message has been kind of acknowledged. So that's kind of how, at a high level, that's how workers work. They just are message passing from the client, from the main thread to the worker thread, do some processing, send the result back to the main thread. And kind of the core premise here is that we're trying to maximize the time in the main thread that we're just not doing anything. Like that's the ultimate goal, is to do as little as possible in the main thread. And the reason for that is that we want to be able to handle these user interactions, and we want to be able to render new content to the screen. And so yeah, not block the main thread. But it would be a little bit disingenuous of me to tell you that workers are going to solve all of our problems, because it's not true. And the reason for this is that workers have a bunch of limitations. So aside from, first of all, everything that you're doing now is currently, like if you put it in a worker, is now asynchronous and you'll now have to have this whole message passing system between the main thread and the worker thread. We also have another set of like hard limitations that we can't get around. So the first one is limited transfer types. So we can't send things like functions, we can't send errors, we can't send regexes. There's a whole host of strange things that you can't send. We also have this problem of transfer time. So if we have big blobs of data, say that you've got a big tree of data that you've got from a server somewhere, or that you've generated in the main thread, now you're trying to pass it to the worker thread, and there's a cost for transferring that data, and the bigger the data, the more the transfer time. So you can actually kind of shoot yourself in the foot if the data is too big, because you end up increasing the amount of work that's happening on the main thread now. And the last core problem with the workers is that they can't access the DOM. And as you can imagine, a lot of the time as web developers, one of the core things we try and do, if we're lucky, is update the screen. So if you're in a worker, that's just not going to happen. So yeah, so workers are super cool. Like it sounds really bad, but workers are great. But they do have their limitations, do have their downfalls. So it's worth pointing those out. And there's some other cool things that you can do. So like I was saying in that first, when I showed you the code example, you would have seen that I had to point it at an individual JavaScript file to run that in the worker. And that can kind of be a bit annoying, because you might not it's not very dynamic. You have to be very explicit up front, this is the file that I want to run in the worker. But there's actually a massive hack that you can use, which is to create like a blob in a data URL, and then you can like inline workers, because it like tricks the browser into thinking that it's a file. And then, so there's a guy called Jason Milner, and he's written this really cool library called Greenlit. And what it allows you to do is you can take any asynchronous function, and then you can turn that into a inline web worker. So all of a sudden, you can kind of have multi-threaded code. Just like you can kind of treat async functions as threads, which is kind of cool. But again, this kind of has some limitations. But yeah, so this example here, what we've done is we've just fetched some data from the server and then returned that JSON into the main thread, and then you've just logged that out basically. And another cool thing that I wanted to talk about is this thing from the AMP team. This thing called worker DOM. So one of the problems that I was talking about with workers is that you don't have DOM access. There's no way to access the DOM. So what worker DOM does is it mocks the API of the DOM. So if you were to get element by ID or whatever it might be, and then it basically passes the message along to the main thread and executes it on the main thread. So the cool thing about this is that you could, there are examples where people have got React running in a worker, and then what it's doing is it just passes little messages back to the main thread to update things. And this means most of your business logic can be happening in a worker, but you don't have to think too much about this DOM limitation. It's pretty cool. You should check it out. And it also has some nice properties, because it's all happening asynchronously, it can batch up operations. So for example, it uses request animation frame to ensure that your DOM updates all happen in frame batches, which is pretty cool. So there's also this kind of thing that we talk about the main thread. I've spoken about the main thread, and people often talk about the main thread quite a lot. But in the actual browser itself, there are kind of other threads that exist, and they're quite cool because they allow the browser to offload some of that work from the main thread. One of the examples of this is the compositor thread, which is pretty cool because it essentially, at the beginning in the event loop, I was talking about these render steps. Well, there are certain operations that you can do, and you can basically offload these to the GPU, and via the compositor thread, you can offload them to the GPU, and just means that they're a lot quicker to run, and they keep they do less work on the main thread essentially. The CSS properties that kind of use that compositor thread and kind of skip some of the render steps are translate, scale, rotate, opacity, and CSS filters. So you might sometimes see people like performance advocates talking about like cheap CSS properties or CSS properties that are cheap to update, and the reason for that is that they use this separate thread. They use this compositor thread, which offloads work to the GPU. Cool. So now for the future. I've talked a little bit about the future because I talked a bit about the what's going on with hopefully going on with kind of scheduling API and some of the work that Facebook's doing with Chrome to have this scheduling API. But I wanted to talk a few things that I've seen that are coming up, which I think are quite cool and hopefully should take some work off of the main thread. So the first of which is some of you might have heard that Edge is moving to Chrome, or Chromium, sorry, which is what underpins Chrome as well. It's the engine underneath Chrome. And the interesting thing about Edge is that Edge actually had did a lot of really cool stuff. So one example of something that Edge did really well is scrolling. And the reason that scrolling in Edge was so smooth was essentially that the scrolling happened on the, I was just talking about the compositor thread. Well, scrolling happens on the compositor thread. So if you have scrolling wouldn't be blocked. If the main thread is blocked, because it happens on the compositor thread, you could still scroll, even if there was some big, long, massive 500 millisecond task that's happening on the main thread, scrolling would still be smooth. So Edge are now putting some commits into Chromium to try and translate some of that work into Chromium, so that will benefit users of Chrome as well. And they're doing a bunch of other stuff as well, but this was the one I thought was super interesting and kind of relevant here. So another thing is this kind of standard that's been proposed. I'm just going to call it blocks because I don't know how to pronounce. Is that an umlaut, I guess? Blux. But essentially, I was talking about greenlit, which is this concept of inline workers. This is essentially the same premise, but as a native browser specification. So you could write a function and assign it to just run in a separate function natively, at the browser level, rather than using these kind of crazy URL data blob hacks. And I personally think that'd be super cool because then you can start just leveraging threads really quickly in your code without having to think too much. So I think that would be really cool. Next thing is this things called worklets. So worklets are specialized kind of workers that focus on one particular thing. So some examples they've got on here are a paint worklet. So you can have imagine you have a CSS, a background, but you want to dynamically generate that background, maybe from the CSS canvas the canvas or something like that. Well, you can use a paint worklet to do that and kind of in certain browsers offload that to a separate thread. Similar kind of thing for audio work generally is, I've not done much myself, but I've been told is very main thread intensive and you can end up blocking the main thread quite a lot. So you have a separate kind of very specific worklet that's specialized for doing audio work. There's some other ones like animation worklet and layout worklet. So there's all these, there's increasingly these kind of specialized worklets that allow you to do certain types of work kind of off the main thread. This is kind of wrapping up now. Takeaways. I guess, so the core takeaway here is that I guess my main point is that like what we end up doing a lot when we build web applications is doing a lot of stuff kind of up front and doing a lot of work in general. So if we can avoid doing that and kind of allow the user to make sure that we can interact with the page, then that's ideal. But in practice, what that means is that kind of avoiding long tasks. So if you have work that can be like chunked up, just trying to chunk it up, maybe using one of the even if it's just set timeout and just chunking it up using that, or using something a bit kind of cleverer with request animation frame or request idle callback. Kind of, can you put the work in a worker? So if the work doesn't touch the DOM, there's a pretty strong chance that you can actually just completely take all that work off the main thread and put it inside a worker. And yeah, the last thing is, can you do that work? I already mentioned this already, but can you do that work in idle time? So can you use something like request idle callback to offload that work to a time when the user is, when the browser is not doing anything. Yeah, so it's I guess just kind of trying to think more critically about the work that we do. Like when we write like JavaScript code, like when does that work happen, and in kind of like what size quantities is that work happening, so to speak. And kind of the last thing I wanted to talk about is this idea that like increasingly like browser vendors are doing like as much as possible to move work off of the main thread for us. So some examples include, at the beginning, I was talking about the download, parse, compile, execute, like steps for JavaScript. Well, Chrome now does a lot of stuff to try and do the parsing and compiling off of the main thread so that it's less blocking, which just means that everybody's websites just get faster for free because all of the parsing and compiling happens off the main thread. So I already talked about the compositor scrolling that's hopefully coming to Chromium on Chrome and Edge, thanks to some of the work from the Edge engineers. Another example is if you've come across service workers. So service workers allow you to do a bunch of stuff. For example, run your application partially offline, and it can do that by like caching responses. And if you cache JavaScript in a service worker in Chrome at the moment, you completely skip the parse and compile time because it caches the bytecode up front. So you get like on repeat visits, it's like going to be even faster, and you don't even like that's just for free. That's just from using a service worker, which is really cool. So there's just like all this stuff that's happening, like even at the browser specs and the browser level, which is having like impacts and kind of helping us, like help do less work on the main thread essentially. So yeah, a little bit under, but that's me. So thanks a lot.
Very valuable presentation. I have a question regarding the raster thread which was on the slide.
Yeah, sure.
Can you explain about more?
Yeah, I can do my best. So to my knowledge, I think the compositor thread will composite all the layers in kind of your frame, and then the raster thread actually turns that into like a raster image and commits that to the GPU. So it basically rasterizes whatever has come from the compositor thread. Any deeper than that, I start to lose understanding. So
it's like a bundler of those actions which need to be performed and sent over to the GPU.
Yeah, I think it just kind of like takes the vector, like this is my understanding, like whatever the vector layout that has come from the compositor thread, because obviously like vectors are just like points, lines, polygons, and it turns it into something that is like pixelizes it, so rasterizes it, is my understanding. I might be slightly wrong about that.
Thank you.
No worries.
Yeah, thanks for talk. I got a question. So there is that CUDA technology from NVIDIA, and as you mentioned before, the graphic works through the vectors. So is there anything in JavaScript world which works with the CUDA technology? Because CUDA, that technology,
CUDA.
Yeah, they supposed to accelerate a lot of like mainstream tasks, Like you give them, like, let's say a huge array and a reduce function, and it will just complete way faster than it could complete on CPU in general.
So, again, not my area of expertise, but there's a thing called gpu.js, and I think what that tries to do is essentially what you're talking about, which is takes work that is, if you're just doing lots of stuff with like arrays, it can essentially, instead of making that CPU bound, makes it GPU bound. That's the like depth of my knowledge when it comes to that kind of stuff. But what I would assume that does is it uses WebGL to process data, would be my guess. But yeah, so check that. It's called gpu.js. That's it.
Sorry, one more question. That's regarding the backend node. So, for example, Express and then those workers.
Yeah.
So, is there any way that Express start assign any request to the specific worker, so it doesn't block a main thread? Because for now, by default, if your endpoint, let's say you write a loop of billion, it do not start actually give a feedback on anything else till the main thread is blocked.
Yeah, so with Node, you have a slightly different scenario because you don't have to render anything. So the whole render steps and all of that is just disappears. You're just processing tasks and micro tasks, which is like promises, basically. In terms of workers, I know, so Node has experimental support for workers. And I think in Node 12 that just came out today, it's becoming very close to non-experimental. So there will eventually be support in like LTS release Node for workers. But as it stands, like Node is just like a single threaded thing that will it just uses the event loop to try and tackle that concurrency problem, basically. Yeah, I'm not like a super Node expert, so I don't know. Maybe the Node event loop is slightly different to the event loop in the browser. Like the behavior might be slightly different. I don't know.
So the edge case which I found is if you got an endpoint which takes a little bit more time than, let's say, 10 milliseconds, and it blocks your thread, everything else is blocked, right?
Yeah.
So, and if someone hits a badly written endpoint with some edge case, your pod is dead, right? And it still give you like a good connection because it expects that, oh, I'm just giving back something but a little bit later. So the load balancer will simply bypass it and it still direct you to the node which is blocked.
Yeah, I mean, that's the problem when you have a single threaded backend like application. Like Node is just it's a single thread, right? It's like just an event loop. So if the thread's blocked, then so there's a thing called, have you heard of PM2? It's like a process manager for Node. And so you can spin up the same application on multiple cores. So what it can do is it will just round robin and send each request to like a different core. Okay. So yeah, check out PM2. I'm not like a Node expert. So, but yeah, it's worth checking out PM2.
Is that Amazon feature?
I don't know if they have it on it. It's just a Node package, but they might have some sort of support for on Amazon. I don't know. Yeah, it's a really good question because it kind of comes back to what we were saying about like ultimately as a developer, your main goal is to update the screen. So a lot of the work that you do day to day is to try and do that, right? So most everyday tasks kind of end up touching the DOM at some point. So what you were saying, things, like CSV parsing, another maps is obviously quite a cool one. So if you're doing things with lots of points and polygons and lines and you want to be processing that off like the main thread, then that's quite a good use case, but again, quite niche. There's things like you could do state management in a worker. So there's examples of doing you could have basically like Redux or MobX in a worker and then it just pass back the results. Things like doing IndexedDB. If you're doing any kind of persistent state like storage in like IndexedDB, then that's quite a good use case. Yeah, it's kind of something you have to do on a case-by-case basis, because the main question is like, does this update the DOM? I mean, another good example is doing a fetch, and then if, say for example, you have a third-party API that brings back some massive blob of JSON, and you're like, yeah, I only care about like one subset of this, where you could do the fetch in a worker, get the response, traverse down the tree of JSON, and then just pull out the bits that you want, and then send that back to the main thread. So if you have like massive objects, that's going to give you quite a nice little performance boost. But yeah, you're right, it's quite hard to, because it's so problem specific, it kind of, there aren't just necessarily like little generic things that you can always put in a worker, because if you touch the DOM, then it's a write-off.